was just first see if there's any particular ones that were vexing. And then after that I can say a few words about the other ones.
Alright, number 1 through 10. Go ahead.
Yeah, let's just start at the beginning to see how far we get.
Okay. Well, actually, one, there's not a whole lot to really discuss. Because, so for this one, I'm just going to, the general approach is just going to be when is gradient going to be equal to 0. And once you figure out the points where that happens, then for each critical point you find, there's the second derivative test. So we had all that's in lecture 9. So you check whether that's positive, negative, or 0. So if it's negative, that's a saddle point. If it's positive, then you check just the fxx by itself. So both these are positive, it's a min, or it's a max, and here, inconclusive. So we're just going to find the gradient equals 0 and classify all the points. Yes? Oops, that's on tape, isn't it?
No.
Okay.
When you say it's greater than 0 or less than 0, it's a saddle point. You mean what's less than 0?
This.
Function itself.
This expression.
That's
Yeah, and yes. So if we check this, and only if it's positive do we need to then check this as well. Because when it's positive, it could be a min or a max, and we got to figure out which. So, yeah, so there's really not a whole lot to this one. But 2, that's a bit more involved. Okay. So this is a good old Lagrange multiplier problem with multiple constraints. So the 2 equations that are given are the constraints. So you have this constraint, the first one, z squared minus 4x squared minus 4y squared is equal to 0. And 2x plus 4z minus 5 is equal to 0. So you're trying to find points x, y, z that satisfy both of those constraints and are closest or furthest from the origin. So what is the actual function that you're trying to find a max or min of? Because all we have written down here are the constraints. Right? So you're maximizing, minimizing distance from the origin. So what function would that be? Given any point, what function tells you the distance from the origin?
Distance function?
Which would be?
Distance function.
Yes, which would be?
x2 minus x1 squared plus y2
yeah,
minus
you're
y1
right.
squared.
But yes, but it's distance from the origin.
So it'd just be x squared.
Pythagorean theorem?
I know what we're talking about. Magnitude.
Yes.
So it's square root of x squared plus y squared plus z squared.
Yeah, that's the distance. Now, because we could actually just throw out the square root, you don't really need to worry about that. Yeah.
It's
If you minimize the maximize distance squared, then that's so. Yeah, so your function is just gonna be x squared plus y squared plus z squared. That's what you want the max or min of. So to visualize what's going on here, so this first equation describes a cone. And the second one describes a plane that's going to cut through the cone. So you get something that looks like this. So, so the intersection of the two, marked in green. So on this ellipsoid thingy, there'll be 2 points. That'll be closest or furthest away from the origin. So you need to find those 2 points. And then what you can do is, once you find them, really what you're going to be finding is constrained critical points. You'll just plug them in here into F and see which is a smaller, which is a larger. Okay. So, to carry out the method of Lagrange multipliers, you have gradient of F is lambda 1, gradient of G1, plus lambda 2, gradient of G2, for some lambda 1 and lambda 2. So if you take this and write out everything, what you're actually going to get is a system of 5 equations. So gradient of F, that's going to be 2x, 2y, 2z. Gradient of G1 is going to be minus 8x, minus 8y, 2z. Gradient of G2 is 2, 0, 4. So, if these 3 equations, then must be satisfied by x, y, z, lambda 1, lambda 2, but you also have the constraints, so you have to include these. So you want to find x, y, z, lambda 1, lambda 2. That satisfy these. So you have 5 equations into 5 unknowns. So wherever you get this or not is really going to boil down a lot more to your algebra than your multivariable calculus. But isn't that always the case?
And it's not cool.
Is that dot 2 dot 4? Is that times?
Oh, yes, it's multiplication.